Hi, this is Mrs. Roble. This is Chapter 12, States of Matter, Part 4. So in the previous slides, we looked at kinetic molecular theory of liquids, and we looked at attractions, intermolecular attractions, such as dipole-dipole and hydrogen bonding. Now today we're going to look at a different type of attraction between liquids. It's called London forces or induced dipole. You may notice that certain liquids, they don't necessarily stay a liquid for long periods of time. And I just want to show you, like hand gel. Didn't you ever wonder how come hand gel, it doesn't stay a liquid for very long? And we're going to look at why. So here we have an example of a nonpolar element, and argon is an example here. And when you look at the molecule or the element, it has blue dots, and these blue dots represent the electron density that is found around the element. Now something interesting happens. We have what we call a temporary dipole. So this is different than the last one that we talked about. That was a permanent dipole. This is temporary. So what happens is the electron density congregates to one side of the atom or the molecule, and then the other side of the atom or molecule is actually left with less electron density, and it acquires a temporary positive charge. What does this mean? Well, one element or molecule can actually induce or force another atom or molecule to have the same kind of arrangement. So notice that this electron density over here forces this other atom or molecule to push its electrons on the opposite side. So this is what we call an induced dipole. So induced dipole is a weaker attraction than what we talked about with a dipole-dipole attraction. So please remember, we have one atom or molecule that has this split-second arrangement of electron density, and it forces the second element or molecule to acquire the same type of arrangement. We could have, like I said, one molecule forcing another molecule to have the same situation here. So notice we have hydrogen. One hydrogen atom bonded to another has less electron density, and it forces another element or molecule to acquire the same kind of induced dipole. Just like we saw with water yesterday, they can rearrange themselves so that the opposite charges are facing another molecule with a different charge. That way they can stay together in a close arrangement. And like I said, this is a very weak attraction. It is not a very strong attraction compared to dipole-dipole. So what does this mean? That means that this is temporary, and it's very weak, and it causes a nearby molecule to acquire this property. And this actually affects the boiling temperature. So a substance that's a liquid that has a very strong attraction with itself is going to have a higher boiling temperature. So something that has a weak attraction, such as induced dipole, is going to have a very low boiling temperature. So here we have three substances, and notice the very first one, it has hydrogen in it but no oxygen. So because of that, it has induced dipole attraction with itself. And as a result, its boiling temperature is a negative 161. Water, which has hydrogen and oxygen with a lone pair of electrons on top of it, has a very high attraction with itself, and because of that, it has a very high boiling point. Here we have carbon dioxide. Yes, we have oxygen, but no, we do not have hydrogen, so we cannot have hydrogen bonding. And as a result of it, there's a very weak attraction with itself, so it has a negative 56 boiling temperature because of that. So please note that in order for a liquid to stay a liquid, the attractive forces between that set of molecules, it has to have some kind of energy to cause it to go from the liquid state to the gas state. So the greater the force, the higher the boiling temperature. What does that mean? You have a liquid, it has attractive force, and in order to get those molecules to go into a different phase, be it a gas phase, you have to add energy to the system. That's why with boiling it takes energy. And the interesting thing is, with this process, you're essentially taking kinetic energy and you're storing potential energy when you go from one phase to another. So you're putting kinetic energy into the system, but you're also storing potential energy. Here we have an example of water. So we have water in the liquid phase. We have to put energy in the form of a Bunsen burner, and we're breaking the attractive force or the hydrogen bonding between the liquid water molecules to create these gas water molecules. And as we do this, we're putting kinetic energy into the system, and we're actually storing potential energy in these molecules.